Now, let us restrict ourselves to the case of linear recurrence relations of order 2. Let us take such a relation. A(n) is equal to C1 a(n minus 1 plus C2 a(n minus 2. And we can write down its characteristic equation. T squared equals C1t plus C2. So this is a quadratic equation, and you can use the formula you know from the high school to find its roots. Suppose that this equation has two distinct roots. That means that its discriminant is not equal to 0. So suppose that lambda and mu are roots of this equation. Well, we denote it by 2 stars. While our original recurrence relation was denoted by 1 star. And we suppose that lambda is not equal to mu. For the moment, you can suppose that lambda and mu are both real, but if the discriminant is negative, well, this won't change much, as we will see later. But if you are more comfortable with real numbers, not with complex ones, you can suggest you can suppose that they are both real. Okay, so as we have seen previously, if lambda and mu are roots of this equation, then we have two geometric progressions. 1 lambda, lambda squared, lambda to the third, etc. And 1 mu, mu squared, mu to the third, etc. which are solutions of this linear recurrence relation of order 2. This means that we can take linear combinations of these two solutions. We can multiply them, each of them by a coefficient, and we can sum them up. And what we get will also be a solution. So this means that an, which is equal to capital C lambda to the power n plus capital D times mu to the power n, is also a solution. So right now we can write down a two-parametric family of equations, for a two-parametric family of solutions. For arbitrary capital C and capital D, we have a solution which is a combination of these two with these coefficients. Okay, the question is, are there any other solutions? We'll show in a moment that the answer is negative, that any solution of this equation can be represented in such a way for some C and D. No, for any solution A0, A1, etc. of the equation star, there exists C and D such that an is C lambda to the nth plus d lambda to the nth. Okay, let us show this. By the way, this solution with c and d as parameters is called a general solution. Of this equation star. How to show this? We already know that any linear recurrence relation is defined by its of a given order, in this case of order 2, is defined by its two first terms, a0 and a1. So if we know a0 and a1, we can reconstruct one by one all other terms of this sequence. So the sequence a1, etc., an is uniquely determined by a0 and a1. Let us show that for any a0 and a1, there exists c and d such that a0 is equal to c times lambda to the nth, that is just c, plus d times lambda to the nth. For n equals to 0, this is just d as well. For any a0, a1, there exist c and d such that this is true. That means that a0 is c plus d, and a1 is c times lambda times plus d times mu. So we have a system of two linear equations with variables c and d. We want to find c and d. And since lambda is not equal to mu, they are not proportional. So this system of equations has a unique solution. Well, let us solve it. So from the first equation, this is equivalent to saying that d can be expressed as a0 minus c, and we use this value of d to say that a1 is equal to c times lambda plus a0 minus c times mu. And from this equation we can find c. C is equal to a1 minus a0 times mu divided by lambda minus mu. And d is just a0 minus this value, and we can rewrite it in such a way that d is a0 lambda minus mu divided by lambda minus mu. Note that the denominator here is not equal to 0 because lambda and mu are distinct. This is where we use this assumption. So we have seen that for arbitrary a0 and a1, C and D are uniquely determined by these values a0 and a1 and the roots of the characteristic equation. So knowing these, we can reconstruct the whole solution. It will have the form of an is equal to c lambda to the power n plus d times mu to the power n. This should be mu. Sorry. Where c and d are written, are obtained as follows.